Hello, students. We will start in 2-3 minutes. I'm waiting for the other students. Hello, everyone. So I think nobody is joining like last today. Uh, so yes. So week 10 was mostly focused on discrete time convolution, LCCDE, sampling, and Nyquist theorem. So today we will be dealing with all this. Okay, so for the next 2 hours, I will be teaching you about all these topics. So what I expect you should have the basic knowledge by this time because half of the course we are almost completed. So the topic one, which is a discrete time convolution sum. So the definition of the what is a discrete time convolution sum, an importance for the linear time in varied systems that we already have seen so many times, and a basic intuition and skepticism. Like, is this always computationally feasible? What do you think? So we have discrete time convolution because convolution basically is minus infinity to infinity, x1 of tau, x2 of t minus tau, t tau. What do you think? What will the output be? It's x1 t convolution of x2 t, and you have output as xt. Since you are doing the integration over tau, so you'll have the output as xt. Similarly, if you to say the discrete time, the discrete time will have the summation, it is replaced by summation and x1 or h, whatever, because input we have xt, sorry, here it will be n because we are talking about discrete time, xn, hn, and this is y. Okay, so input signal, hn is a impulse response because this is an impulse response. Impulse because uh, why we call it this is the impulse response because when xn is equals to del t. Yn is equals to h of n. Okay, yn is the output signal. And this goes from minus infinity to infinity, xk, h of n minus k. Here we are doing the integration with respect to k, not n. That's why we are getting output in terms of n. So these are some mathematical details. Firstly, linearity, you have this linearity, then time invariance. Just go through this by this. So we have invariance, time invariance, skeptical notice. Convolution sums can be long, and real-time systems often use the efficient algorithms like FFT based convolution. Okay. So we have shifting xn results and a shift in by n. So I would like to show you some of the convolution methods in MATLAB. So that you'll have some basic understanding of convolution. So I hope you are able to see my screen. So I hope you are able to see my screen. So I would like to show you. See this. So we have why convolution matters. Just a second.
Important for signal processing, image processing, statistics, engineering, physics, the list goes on. So it's worth it for us to
In order
spend
to
some time
find the
deepening our
application
understanding.
of convolution with respect to image processing, signal processing, as we are dealing with the signal processing, I'm just showing you the small video and then we will go through the example course and I have prepared some of the contents.
Of what it is and when to use it. And that's what we're going to do today. Let's explore why convolution matters. Convolution is an integral defined by this equation here. Now, this might look scary at first, but let's break it down to get a better understanding. Convolution calculates how the shape of one function, f, is modified by another, g. It slides one function over the other, multiplying and integrating their product at each step, effectively blending them together in some way. Think of f of tau as capturing a snapshot of the first function at a specific moment, tau. G of t minus tau flips the second function around and shifts it to align with the moment we're considering. By multiplying these two snapshot values, we're calculating the degree of their interaction, essentially asking, how much does the shape of one function at this moment affect the shape of the other? The integral then tells us to add up all these interactions over every possible tau, giving a complete picture of how the entire first function is transformed by the entirety of the second. Still confused? Visually, it looks like this. We start with two functions, f and g. To convolve them, g is flipped in time, and then we sweep it across the entirety of f. For each moment in time, as g is swept across f, we multiply the two functions together and then sum the result. Essentially, we're scaling one function by the other, that's the multiplication, and then returning the area
So how the convolution is getting through the area, you have to see like this.
under the curve. That's the integral. So despite the convoluted looking equation, calculating a convolution is pretty straightforward mathematically, just multiplying and summing two functions across time. And it's even more straightforward with the conv function in MATLAB, which we'll be employing to calculate our convolutions today. Here we're using the continuous time convolution integral, but there's also a discrete time equivalent, where the integral is replaced with discrete summation. The discrete time version is hugely important in science and engineering because of how prevalent digital signals are in those fields, but fundamentally the concept is the same in both domains. Okay, now that we have a better understanding of the mathematics behind convolution, it's time to get into why it's so important to so many different applications. What exactly is it doing for us, and which types of problems does it help us solve? Well, let's dive in. Let's get into an example where we can see convolution in action. It's one you may have heard of before. Sound! Imagine you're standing in a big, empty, and quiet room, and you let out a short yell. We'll call that an impulse. Those sound waves created by the impulse will leave your mouth, bounce around the room, and dissipate over time. We'll call that the impulse response. So, what you hear after you yell is an initial loud sound, which then tapers off as you hear some of the quieter reflections from around the room until the sound is gone completely. The shape and materials of the room define what this response looks like, and by changing the room, we can get different responses. For example, a small room with a lot of carpet and furniture would not reflect much of the sound, whereas a large room with a lot of glass would be very echoey. What does this have to do with convolution? Let's say you yell, and before the room's impulse response, G, dies out completely, you yell again. This creates a new impulse input function, F. The total sound in the room will be the combination of the new yell plus whatever is left over from the first yell. This means that at any moment in time, tau, we can figure out what the room sounds like by simply convolving the impulse response of the room G with the inputs into the room F. Using the conv function, we take the convolution equation, add in the signals F and G, and the solution produced is the calculation of the total sound in the room. We could even calculate what the room will sound like over time with any input, like with continuous talking or with music playing, simply by knowing which sounds are being injected into the room, function F, and the acoustics of the room, function G. It's just a convolution of the two. Let's take this specific example of sound and expand on it. A sound wave is just one of endless types of signals all around us, and convolution is vital for processing and filtering these signals. So far, we've just been observing sound waves as they propagate throughout a room, but what if we wanted to intentionally design a response for the sound waves to follow? Physically, you'd change this by altering the layout or makeup of the room, which would change the room's impulse response. But let's say you had a signal you wanted to alter mathematically. You do this by creating a filter. And like the room, we can understand the filter by looking at its impulse response, which we then apply to the signal through convolution. For example, let's say you have a digital signal from a sensor, like a microphone picking up sound waves, and you want to filter out the high-frequency noise. This can be done with a low-pass filter, and a simple version of that is the moving average. A moving average filter attenuates the higher frequencies by smoothing over abrupt changes or sharp peaks in the signal, while leaving the lower frequencies alone. If we put the initial signal F and the impulse response G into the conv function, we can determine the filtered result, a moving averaged version of the original signal. Now let's listen to the results. As the filter gets applied to my audio, you can hear that the low frequencies remain while the high frequencies are eliminated, resulting in my voice now sounding rather muffled. When it comes to filter design, we're often concerned with the frequency characteristics of a signal, which can be hard to visualize and design in the time domain. And up till now, we've only talked about convolution as being a time domain function. Thankfully, there's a nice symmetry between convolution and multiplication for the time and frequency domains. Convolving two time domain signals is equivalent to multiplying those signals in the frequency domain, and the opposite is true as well. Convolving two frequency signals is the same as multiplying their time counterparts. So just keep this in mind that if you're doing filter design, you may never calculate the convolution integral directly, but the same concept is being applied when you multiply two frequency signals together. As this moving average example shows, we can design any number of interesting and useful filters for processing signals simply by shaping the impulse response. Alright, we've talked a lot about one-dimensional signals, like sound waves, but what if we add another dimension to our signals? Turns out that convolution can also be done on two-dimensional signals. And what is a two-dimensional signal? Well, images are. We just discussed getting the moving average of a sound signal, and we can do the same filtering scheme with an image. This is called a blur filter. To apply this to an image of yours truly, we take a kernel, a 2D filter with specific size and values in it, and pass it over the image, multiplying and summing pixel by pixel to create a product which is a modified version of the original image. I'm sure we've all seen a blurred image before, and this is precisely what it is, using a kernel with values like these to create a moving average of an image, filtering out the high frequency details and producing a blur effect. In addition to blurring an image, we can also perform edge detection on the image through using a kernel with values like these to highlight areas in the image that have stark changes in color values. Not only can we detect edges, but we can refine them as well with a sharpening filter. Applying a kernel with values like these causes edges to be more defined, thus adding a sharpened look to the image. The foundations of image processing are powered by convolution, and the mighty kernel can be used to manipulate or even analyze an image in all sorts of ways. Advances in artificial intelligence have taken image convolution even further. We just learned that with some clever kernel design, we can do things like detect edges and sharpen images. If we use a common deep learning model, like a convolutional neural network, machines can take data and learn how to design kernels for different tasks. For example, we could load millions of labeled images of various animals into a computer. Then, the computer uses an algorithm to iteratively design and optimize hundreds of kernels. These kernels are then used to process images, which allows the computer to tell the difference between a dog and a cat. All this is built on the simple yet powerful operation of convolution. Convolution is all around us and ridiculously important. In this video, we've only scratched the surface of all the ways it impacts our lives. In fact, maybe you can think of some other applications that rely on convolution. If you can think of any, leave them in the comments below. For more information on convolution in MATLAB, check out the MathWorks Discovery page for convolution, as well as interactive on-ramp courses for signal processing and image processing, all linked in the description. Thanks for watching, and I'll see you in another video.
Okay, so we saw the practical implications. Okay, I will just tell you some of the codes. These are the convolution and image processing. What I want you to go through is I want to you to So some network issue was there. Let me again share my screen and show. See, some network issue was there. So So basically, if you say what is a linear and circular convolution, so this example shows how to establish the equivalence between linear and the circular one. Just linear and circular are the fundamentally different operations. However, they are the condition under which linear and circular convolution are equivalent. So since we are talking about DFT and uh, the time series data, so the establishing this equivalence has important implications. For two vectors x and y, circular convolution is equal to a discrete Fourier transform. Okay, so it is equal to discrete Fourier transform of the product of the vectors of DFTs. So knowing the condition under which circular convolution are equivalent allows you to use the DFT to efficiently compute the linear convolutions. So the linear convolution is n point vector x and the L point vector y. So it has the length of n plus L minus. So see, you have two vectors x and y and compute the linear convolution of the two vectors. So x is this and y is this. So this is giving the output as length. C of length is convolution. Length is 3, 4 plus 3 minus 1 because this is 4, this is 3, and then minus 1. So I would like to so from there you can directly copy. It will take some time. So I'm writing the command into here. So directly writing here in the command window, you can just open this. So this example shows, suppose I want to run this. So this I am running here. And this is what it is giving. Since I kept semicolon here, so that's why it says like equal. So output you can see. We have output 2, 5, 10, 8, 8, 3. And this has output of length this 4 plus 3 minus 1. So how this actually works? Okay. So if we pad both vectors to zeros to length 4 plus 3 minus 1, and if you obtain a DFT of both vectors, multiply the DFTs and obtain the inverse DFT. So how this gets? Let me keep it there. See how it looks. 2, 5, 10, 8, 8, 3. And if you want to plot, let me plot. So the linear convolution is filled. So this is the linear convolution filled one. And the circular convolution. So okay. So we have linear convolution one graph, circular convolution and the other graph. So you can clearly see both are not same or it's same. What do you say? It's same. Okay. In this case, it is same. So, so again, it's giving some values. So yeah, this is what MATLAB does to you. And in the workspace, you are having so many variables. So again, you can go through this, just check them. It's visible to you all. So I'm sharing progress. So I'll get back to this part. So we have seen so many examples. Okay. And as I was telling the real life example, it's filtering and audio processing. Then if XN is a input signal, by HN is a filter impulse response. The convolution gives the filtered output. The practical concern is long filters had computationally high load. So that is our concern. So what do you think? Is that really a concern? Is that a concern? No. So we have already seen this topic. So this is the example problem. You have to find the convolution. How will you find? This is very simple. Xn is 1, 0. Uh, what is that 1, 0? It's impulse function, right? It's delta function. Where Hn is you have a unit step function. How will you solve this? The convolution. How will you solve? So let us see how will we solve. So these are the step-by-step process that I have solved. I have done for you. First of all, simple same procedure. Okay. So I hope it's clear. So the SK is non-zero and K is equal to 0. So by following simple formula, what output we are getting? So hence y is equals to 1 for n is equals to 0 to 1, 2, and otherwise it is 0. I will ask you to solve this question. How will you solve? It's very simple. What will the output? So these are the step-by-step solutions. Okay, so if we combine carefully, we'll get the output. But again, what was the problem? It's xn, which is a del n plus del n minus 1. And hn is del n minus del n minus 1. So we have to find the circular combination. So if you see, you have xn, which is 1. Sorry, if I plot, so it's just del n x, del n minus 1. So you have this output. Whereas hn, del n minus 1, this is minus 1, this is 0. And this is 0. If fine, you have to simply follow the steps and we have to combine the steps. Evaluating the sum. So sum is this one, plus. So if we go to topic number 2, which is further examples of discrete convolution properties and real like tie-in multi-stage filters. So key properties are this. I would not like to repeat it again, but yeah, if you have any doubt, this. So, okay. So commutative, associative, distributive, it's similar to the real time. So there are some additional properties, like shift properties. You have xn, yn is equals to xn convolution with yn. Then you have this x y of n minus n naught. Then if you got if you shift it to the output, it will shift to all the inputs also. If you shift it to one input, it will shift to all the inputs also. So it's very important. And also causality in convolution. So we have xn and yn as causal. So yn is also causal, suppose. If inputs are causal, it is also causal. And energy consideration is that convolution can spread out the signal energy in time. Okay. So that's but it's very strange example that is multi-stage filter. Anyone can tell me what is a real life example of multi-stage filter? So in audio processing, actually, we might have an equalizer that is a low pass and reverb that is an echo filter in series. So associativity of the convolution means you can convolve the impulse responses first and then apply ones, okay, which saves computation but can be large if the filters are very large. So there are some example problems on this topic also. We have X and Y. Sorry, I repeated this again. Okay, so this is the step-by-step solution in this case. So xk is actually non-zero for the 0, 1, 2, or x n minus k is actually non-zero uh for 0 to n minus k to 1. So for a specific n, h of n minus k is equals to 1 if n minus k is equals to either 0 or 1. So if we evaluate the piecewise for different n, so we will have the steps. So going to the example number 2, again, find the equivalent single filter which is having H1 and convolution with H2N, and you have H1N as 1 uh, x del n plus del n minus 1, and H2N is del n minus del n minus 2. Okay, so let us find them. By going with a simple formula, you have H equivalent is simple but not net least. It's a convolution of H1 and H2N. And so H1N is nothing but del K plus del K minus 1 H2 N minus K is del K N minus K minus del N minus K minus 2, because as we know from the time shifting property. And if we expand it and evaluate the terms with the shifting property, and if we combine with the signs, as we can see that, and the final HQN is nothing but del N minus 1, del N minus del N minus 2 plus del N minus 1 minus del N minus 2. Okay, so this goes on. So third topic was linear constant coefficient differential equations, and which is very, very much related to LTI system, and the short form is LCCTE. And the real world perspective is difference equations and digital filters. Okay. So general form of LCCTE, we have this form yn minus 1 to yn minus n, where xn to xn minus n, and a0, a1, a1, and b0, bn are the constants, where the LTI system and plus response will be determined by these conditions. So real system can have the real time varying and non-linear behavior in practice. So if we talk about relation to the step function, We have okay. So poles and zeros determine the system behavior when the impulse response is such an inverse jet transform of conception. So we have real life example, which is a digital audio filter. A simple IIR filter for the pass boost can be written as an LCCTE. Example, yn is equals to Fn plus alpha yn minus n for some given form. So implementation must consider the stability out of alpha less than 0. So these are the example problems. They have L, C, C, D, E. Find the n plus response. How will you find? So y of n is minus 1 by 2, y of n minus 1, where x of n. So impulse response will be given by step by step. So we have x and y and how the HM will be calculated. So we have HN is equals to 1 by 2 power n. Steps are executed. Moving to the second question, how to solve it? So you have again LCCDB, or you have yn plus yn minus 1 is equals to xn plus x minus 1. Find the difference in equation impulse response and common mode stability. I want you to comment on stability. Okay, so let us find out. So we del xn is equals to del n. We get hn is it plus hn minus 1 here. And for n is equals to 0, what we have for n is equals to 1 with what we have, then we will define it for n greater than 1. Okay. Then we will keep things in h2 is equals to minus h1 is equals to 0, h3 is equals to minus h2 and is equals to 0. Then hn is equals to 1, 0. Finite impulse response is equals to actually leading to, because since it is greater than 0, for n greater than uh, 0, which is leading to Bibo stability. Okay, so you don't have values for n less than 1, minus 1. So you have values at n equal to 0 and n greater than 0. So you have Bibo stability. Okay. So topic 4 was the concept of sampling and time signal with impulses, mathematical representation of sampling period, real life example, idealized sampling and analog to digital numbers. Mathematical representation, if we say, what does this sampling mean? So we have practical concerns like suppose impulse at t is equals to NTS fix off the value as x NTS, where XTS is equals to XT summation from minus NT to NT, where del T minus NTS. So the three impulses are actually not realizable. So the short pulses approximates them. So we can write in terms of Fourier transform. That shows that. So real life example is analog to digital converter where sampling is done at every discrete time interval Ts. The output is a sequence of voltage values stored for a digital process. So in practice, a sample and whole circuit approximates the impulse train. So this is very unique term that we should take, or I should say that in reality, sample and whole circuit approximates the impulse train. So there are some examples that I would like to say. And these are the examples which I have taken from the real life example. Okay, so these are the step-by-step process. Like for example, you had xt is equals to e power minus t. The sample when it was trained completed t is equals to 1 seconds. So sample signal you have to find. The sample signal is nothing but x s t is equals to xt multiplied by uh, n equals to minus into infinity x del t minus nts. Okay. So since xt we replace e power minus t ut, so we just have to put the values for t. So for negative, this is what e power. Since if we go inside, t will be replaced by n. Since n will go here, 0 to minus t, it is multiplied with that. So since ut is multiplied, so e power minus n will go inside and del t minus n. For negative n, ut gives the term since xt is equal to 0 for t less than 0. This is again a very good example. We have cos signal and sampled by the impulses at s t is equals to 0.01. So what exactly they are doing? So we are multiplying with the signal with the impulse train. So t del t minus nts. It's multiplied. Okay. Just simple multiplication. So to sample signal is nothing but sample signal is nothing but to multiplication with the impulse train. So how will this xn will look like? So this is what impulse train sampling is. And if we multiply and get the signals, so xn is nothing but x of s nts. Simply multiply with nts will also give it to ignore the impulses. So it will give cos 2 pi n. Oh, that's great, right? Because cos 2 pi n is equals to 1 for all the integer n. And this reveals potential aliasing issues if not carefully analyzed. So we have some 1 for all the integer n. So that is problem. Look at this carefully. The signal reconstruction is a primary topic which forms a discrete samples to continuous time signal. Ideal reconstruction is via sync interpolation. And real life examples or digital to analog signals, we will do that. Ideal reconstruction formula. Is battery is running low. So perfect reconstruction will be possible if we have sync is equals to sine pi x by x. Reconstruction, like if we have the sampling and it should meet the Nyquist criterion. Nyquist criterion is the sample rate should be greater than equal to minimum of 2 into maximum frequency. Important charge. So the constructed signal from x of n is sync t minus nts divided by ts, summation of minus infinity to infinity x n into sync t minus nts divided by ts, where sync is nothing but sine pi x by x by x. Let us see some of the examples. So real life example are this. A DAC uses a zero holder or zero order hold or similar approach to approximate perfect sync interpolation. So a DAC uses a zero order hold or subnet approach to approximate ideal sync interpolation. So zero order hold, it used to approximate sync because sync is somewhat like this. Sync X. So perfect sync filters are not realizable. So practical DAC has slight distortion. And we have this. So XRT is actually the reconstructed sync. Okay. So example one. So discrete samples where xn is equals to del n plus 2 del n minus 1, where suppose ds is equals to 1. Find the reconstructed continuous time signal xrt using ideal synchronic representation. So just by using the formula. So we have xn into t minus 1. So xn sync t minus n ts wherever t is xrt. So xn is about 0. So just putting that's a contrast time reconstructed signal, putting the values. Given discrete samples of xn is equals to cos pi by 2n, where ts is equals to 1. Find the ideal reconstruction. It's not approximation, but it's ideal. So how will you solve them? These are the step-by-step steps. Okay, so just following the steps, cos pi by 2 and t minus n. This is a sum of scaled and simulated functions. So in practice, cos pi by 2 n is actually a repeating sequence of 1, 0, minus 1, 0. So xrt becomes, keeping the values there, t minus 4k minus t minus 4k plus 2, and grouping the patterns of uh, pi by 2 n. So for full closed form, might be complicated, but conceptually it's superposition of sync pulses. So Nyquist theorem, I will tell you what is Nyquist theorem, statement of the Nyquist theorem, aliasing phenomena. Real life example under sampling in audio leads to distortion. So these are the so if x t is band limited to b hertz, that is sampling rate fs greater than 2b is actually required for the perfect reconstruction. Real signal might not be band limited. So aliasing concept does this. Frequency above the half of the sampling rate are fold back to the baseband, which is greater than 2. Okay. Sampling rate. There results in distortion if not filtered out before sampling, which is a common error. Sampling it too late leads to spurious low frequencies. Real life audio. Okay, so this is an example. So this is example one. So a signal with the highest frequency component 5K. The question is a minimum sampling rate to avoid the aliasing frequency. What will be that? And what is the answer? So the answer is the highest frequency is 5 kilohertz. So to make this ratio, the fs should be greater than 2 FM. So it should be basically the minimum sampling rate is fs should be greater than 10 kilohertz plus some margin. So aliasing, I told that if it is if we sample at less than the sampling frequency, so the suppose audio sampling rate is 44 kilohertz. Okay, capturing up to 22 kilohertz. So if you sample less, but the signal has converted up to 10 kilohertz, this aliasing occurs. So anti-aliasing filter is used in practice to remove filters above fs by 2. Example 2. So we have continuous time signal which has two components. Okay. So we have two components sampled at fs is equals to 10 volts. Find the alias discrete time frequencies. So we have original signals at 3 kilohertz, 3 hertz, and 8 hertz. So an increased frequency will be fs by 2. That is, with 10 it's given 5. So any signal which is less than 5 hertz will be no alias. So 3 hertz will be no alias. It appears 3 hertz in the discrete time domain. But if it is greater than fs by 2, so alias frequency is above. So it is fs minus 8. So fs is what? 10. 8 is actually frequency. So it will holding around 5 hertz. So in discrete time, the signal looks like 3 hertz and 2 hertz size. Um, so overall summary is this. The foundation of LTI system in discrete is actually so practical considerations, which is see FFT-based methods are often used. Time varying or non-linear system validate this assumption. Perfect sampling and reconstruction is idealized. Real circuits approximate. Always remain skeptical. So if you have any questions, just let me know. So we'll go through the questions again one by one. It's a direct delta function. Next question. Tell me the answer. Which of the following impulse response corresponds to causal LTI system? What if it's definitely A and U n minus one because it cannot be future. Okay, so these are the steps. Next question. If a signal had xn is equals to 0.5 minus n mu n is input to LTI system impulse response, xn is equals to u. What is the output value? Here's the u, n is the unit step function. Tell Let us go to solution. The correct answer is A, 2 power n minus n plus 1, n minus 1 n 1. So we have step by step output, like output of LTI system. What will be that? It's just a simple formulation going through that. Uh, so here output xk is equals to 0.5 power minus k uk and n minus k is equals to u n minus k simply. So for n greater than or equal to 0, your n minus k is 1. It is greater than 0 for because here it is u. So if you put this formation here in this formula, we'll be getting 2 power k and final output is this. For the calculation, we get this formula. So on to the next question. So let xt be a signal with Nyquist sampling rate, the omega naught. So consider yt is equals to xt plus xt minus 2. So what will the Nyquist sampling rate for yt? What do you think about it? So we have 2 omega and the detailed explanation expert with questions conviction is given here. With the next question. So if we differentiate uh, what will be the microsampling rate and XTB signal with microsampling rate 2 megahertz, what will the microsampling rate for bulb? What do you think? Think about it. Mm, 2 omega not only because taking the derivative doesn't typically increase the highest frequency component. So if xt is band limited to omega naught, then d by dt of xt remains band limited to same signal in the ideal theory. So officially accepted answer was 2. So this is the question. So answer is A. Question number 8. I was not able to see. Draw the figure. So frequency domain representation is comprised omega naught to omega naught. What is the centric frequency must be chosen? So I'll show you the answers. Maybe you can just have. So for the perfect alias, the omega naught, omega should be greater than equal to 2 omega naught. And if omega s is actually strictly less than 2 omega naught, the aliasing occurs. Okay, so omega naught s should be greater than omega naught and should be less than 2 omega naught. These are the same. So discrete time delta is a knocker delta, and causality in discrete system often require n minus n naught factors. And LCCT with non-zero feedback is actually IIR. Nyquist rate must exceed 2 maximum frequency to avoid IDS. Shifting a signal in time doesn't usually change its bandwidth, but follow close definition for Nyquist simply rate in that person. Thank you so much. If you have any question, just let me know. I'm still in the meeting right for you. So I think there is no question, and I have covered almost all the concepts, and I will definitely upload all these things in, in the drive link. And thank you so much for joining. And those who couldn't join, they can still mail me for any doubts. I'm available to the answer. So for the last week, I didn't get any questions, so I prepared for myself. If you have any questions, just do let me know. I am happy to. Thank you so much.